I'm going to finish our discussion of microstrip transmission lines by discussing attenuation in microstrip line. And signals that are traveling in microstrip lines are going to experience signal reduction or attenuation via multiple sources. And these are conductor loss, which is the dissipation of power due to resistive heating, sometimes called ohmic losses. The second is dielectric loss, and this is the loss of power due to current flow in the dielectric material, in the insulation material. And then the third is radiative loss, and radiative loss is the unintentional creation of electromagnetic propagating waves from the surface of the conductor due to surface irregularities. So I'm going to work backwards and start with radiative loss. Radiative loss, if I have a perfectly flat conductor, radiative loss typically won't occur. Radiative loss occurs when there's irregularities on the surface of the conductor. These act as tiny little antennas launching electromagnetic waves from the surface, and therefore power gets directed out of the T-line and into the electromagnetic wave. That can also occur if there are right angles in the transmission line. So here I'm looking at a cross-section of the surface. Well, here I'm looking at a bird's eye view of the shape of the signal path. So maybe that signal path, has two right angles in it. Well, this right angle is going to create a radiative point, and this right angle is going to create a radiative point. So I can reduce those by switching to a geometry that looks more like that, getting rid of those perfect right angles right there reduces radiative loss. It doesn't eliminate it, but it reduces it. So radiative loss, we can mitigate it just by properly drawing the transmission line path and by choosing smooth surfaces. So we don't really care about radiative loss because we can mitigate its effects. Conductor loss and dielectric loss, on the other hand, we have to take into account. So because these are the only ones left, we typically approximate total attenuation in the conductor as consisting of two parts: attenuation due to the conductor metal itself, plus the attenuation due to the dielectric material. So the total attenuation is the sum of the conductor loss and the dielectric loss, and as with our previous discussion in attenuation on T-lines, this is measured in units of Nepers per meter. So let's first look at the conductor loss, alpha sub C. So the formula for conductor loss is that we take the skin resistance of the conductor that we're using, and we divide that by the characteristic impedance of the T-line times the width of the signal trace, W. And this, we've already talked about. This skin effect resistance is something new, and it is the resistance of the material due to the fact that the electromagnetic signal cannot permeate the entire depth of the trace. So we only have a small portion of the trace available to us for conduction, and therefore the effective resistance is smaller due to the skin effect. Our skin is calculated from 1 divided by sigma sub of the conductor, so the conductance of the conductor, times the skin depth, delta, times 1 minus e to the minus t divided by the skin depth, delta. And so we've talked about conductance of a conductor. I briefly mentioned skin depth previously. T here is the thickness of the signal trace. So if I've got a signal trace on top of a substrate that's got a ground plane on it, T is this dimension right here. It's the thickness of the signal path. And the formula for the skin depth, that's in ohms, by the way. The formula for skin depth is equal to 1 divided by the square root of pi times the frequency times the magnetic permeability of the conductor times the conductivity of the conductor. and that's going to be measured in meters. So that's how I calculate alpha in Nepers per meter for the conductor. What about for the dielectric? What's the attenuation to that? That, it turns out, is dependent on the angular frequency, omega, divided by the speed of light. We multiply that by the relative electric permittivity of the material times the effective permittivity of the substrate, minus 1. Divide that by 2 times the square root of epsilon effective times epsilon relative, minus 1, and that whole thing gets measured by something called tan delta Nepers per meter. And this tan delta is that loss tangent that I showed you in the very beginning of the lecture today. It is typically a value that you will get from a data sheet. It is not the tangent of delta. That's not how you calculate it. Calculating tan delta is a little bit beyond the scope, not a little bit, it's a lot beyond the scope of this class. It's kind of an advanced electromagnetic materials question. And so for our purposes, tan delta is always something that is measured on a data sheet and provided to you on a data sheet. It is not the tangent of the skin depth. So don't that would make sense anyway, right? You can't take the tangent of a meter. Tangent has to be degrees or radians. And so clearly it's not tangent of delta. It's just the whole thing is tan delta loss tangent. So that kind of wraps it up. That wraps up our discussion of microstrip. So.